have Pradeep, who is an assistant professor in software engineering at Rochester Institute of Technology, talking about learning a privacy incidents database. So, all yours.
Thank you.
Thank you, Michelle.
Good morning, all. As I said, my name is Pradeep. This is a joint work with Dr. Jessica Staten at NC State and her students. What I'm going to talk about today is about learning the privacy incidents database. To get started, so broadly, the motivation for what we're doing is, think of some questions that I would like to answer, think of how we would answer those questions. Like, when did the awareness of cyberbullying increase? How many publicly available known incidents are there in 2014? Or how many public privacy incidents involving a certain company were reported last year? How many privacy incidents were caused by software bugs? How many were successfully litigated? So today, if you want to answer questions like that, the meta question is actually how do you go about answering them? So the answer is actually there's no easy way of doing that. And even more, who should care to answer questions like that and why? Basically everybody should care for answering questions like that. Researchers want to answer such questions because they want to inform technological improvements. Research community and then the organizations care for answering questions like that because it's increasingly common to have instant response teams in organizations. So when there is an incident, they want to know what is the best way to respond to it. So they need to be able to answer such questions as well. And even the government needs to answer questions like that to inform better policy. So, but you may ask actually, these questions are not, they're inherently difficult to answer. So what can we do in order to answer them? So one thing that I've been doing, or we have been doing is, so we started with a bunch of privacy incidents, whatever we can find on the internet, or also from whatever sources you can find them. So do an ad hoc analysis to see actually if there is some kind of a pattern in the way these incidents manifest. And it happens that there are quite a few patterns that you can observe even with an ad hoc analysis. Like for example, we see that there was an incident where WhatsApp was collecting contacts information from like the mobile app, and it happened in 2014. And we see that a similar thing happened, like a similar incident happened with Uber in the following year. So incidents keep repeating, like similar incidents happen. And then in many cases you may have different problems, but the underlying root cause is the same. That's another pattern that you can observe. Again, when you look at this, you can observe from the incidents as well as from what users discuss about what they want about a particular app across forums. For example, here see that many people, when it comes to social networking kinds of apps, people want to be able to change certain things in their profile that their connections don't see. This is across different applications. So there's the common root cause for things like that. Similarly, even like in design patterns, when I was talking about not the software but the privacy kinds of patterns, you see that many problems are because the defaults are not obvious. So they seem to have, for example, here the default options, they are publicly shared, and that's something that's what users don't want. So the gist of this analysis is that although some of these questions are, although there are numerous incidents, there are a few underlying patterns that lead to these incidents. And what we're trying to do is, can we build a database of privacy incidents? So you have various kinds of these incidents. You can find them on the internet using various kinds of search. There are reputations, there's so much of information overload. Can you, if you systematically curate a database of privacy incidents, can you facilitate some of the analysis that I talked about in a more systematic way? That's the broader agenda of what we want to do. And with respect to the database itself, we already imagine it as a Wikipedia-style database where people can contribute incidents to it, but still there will be moderators who will add what goes into the database and what doesn't. And on top of that, we can do like researchers and this publicly available researchers can download the data sets or do whatever analysis they want to do. So that is the broader agenda for what we want to do. So The question is, aren't there already such databases around? Aren't there already such information sources available? For security, probably yes. Again, even there, I don't think there are very systematic kinds of databases. There are like individual companies may have security breaches kinds of data sets, and there used to be VS Havens, which is closed now. But the challenge is, like, there are many privacy incidents which don't necessarily qualify as security incidents. So those things don't necessarily are available in the existing security incidents databases. Like example include like cyberbullying or re-identification and social media oversharing and things like that. They are not available in any existing security databases. So, so we want to capture that in the privacy incidents database that we are planning to build. So we have a prototype of the database available. That's the URL go.ncsc.edu/privacy incidents. We have about 366 incidents that are currently available in the database. You can download them, or you can ask us for permissions if you want to do more things with that. So it's from an engineering perspective, it's a big challenge to curate this database. But at the same time, are there some fundamental challenges that we need to address in order to build such a database? Of course, I'm not talking about problems that we can address once we have the data set available. The questions are actually, are there some fundamental problems in building the database itself? So we see sort of three main research themes that that come across in building the database. So one, we want to first define what a privacy incident is, because it could mean different things to different people. And then once you have a notion of what you want to include in the database, doing it in a fully manual way where only people contribute instance, that's not a scalable model. We need some kind of an automated way where you can populate the database using some of the data mining or machine learning techniques. And eventually, sustainability, like I said, we want to engage an active community of users in using the database as well as contributing to it. That's a challenge in itself. So, in this, in the paper that we have in HoTSoS, it was more about automation. So I'll talk about that at length. And as for definition and scope, we had a paper in USEC recently which talked about what definition we had and how we validated it. I'll briefly allude to it, and I'll not talk much about sustainability because we're still in early stages. We are trying to curate something. So we start with the definition of a privacy incident like this. So we call something as a privacy incident if it has three characteristics. And first, it's an instance of accidental or unauthorized collection, use, or exposure of sensitive information, or it's an event that creates such a perception. And to restrict to the kinds of things that we're dealing with, we say that the information must be in digital form. So three, again, like I said, it's not necessary that everything that everybody considers from different stakeholder perspective, what like a law considers as privacy, what researchers consider. It's not necessary that it includes everything, but this is an approximation. We think this should capture a set of incidents that should be that should cater to a wide audience, is what we think. Like for example, especially the second point, where we are including events that create a perception where the threat is not real, or there's no instance of real damage that has already happened. Law doesn't consider them as privacy incidents. I think in law, the threat has to be either real or imminent. So we also include events which create such a perception into a database. So we did like sort of a validation or sort of a sanity check to see if this database this definition makes sense. We did a mechanical Turk user study where we sought actually end users, like people who are using these applications, whether they think incidents that follow definition of a privacy incident, whether they think that them as privacy incidents or not. And it was a simple survey where we had a bunch of positive and negative articles. So positive articles meaning articles that follow the definitions that we had, and negative articles are those that don't follow the definition. And in a survey, what we showed is we showed the article with the content of, when I say article, I'm referring to news articles. So we showed the news article to the participant, asked them to read through it, and don't tell them the definition yet. So ask them actually whether they think the article is a privacy incident or not. And then you tell the definition that we had in mind, and ask them again whether they think it's a privacy incident or not. And see actually if If the two agree, then we have a decent definition. Otherwise, there are a lot of things that we missed from the definition. So some of the results we had. For the positive set of one thing we noticed that if there is like people didn't change their opinion after they saw the definition. So whether they thought of something as a privacy incident or not originally before they saw the definition and after they saw the definition, they were similar. So from that perspective, we do think that actually people agree to the definition. But at the same time, for the negative side, the overall precision is low. Many of the articles that we thought of as not privacy, people did think of them as privacy incidents. So I won't go detail into, like there are some observations that we did, mainly with respect to regulations or legal events. We don't think them as privacy events because it's just describing broadly what the law is about. Many end users seem to think of them as privacy incidents. And there is the computer security versus privacy. I think that's very intertwined. Like for example, there was an example of somebody hacking into a road sign, which we think is a security incident but not a privacy incident. But many people thought of that as a privacy incident. About the harm being perceived, not real. People agree to our intuition that actually even if the harm is perceived, we can treat something as a privacy incident. Okay. And like I said, the other part of what we're doing is to see if we can automatically identify incidents and populate the database. So, and we need it for large-scale applicability of or an efficient means of populating the database. So we did something fairly simple in terms of the methods that we built, but surprisingly, and also I think it's good or bad, I don't know, it works very well. So I'm going to talk about that. So the broader idea is that we start with a classifier and it goes through whatever information is available in the online sources like blogs or news articles, and it flags certain incidents as potentially privacy incident. And then we have a small set of moderators who look at the ones flagged by the classifier and decide whether they should go into the database or not. We don't want to make it completely automated because I think there are many gray examples. We still want to have a human in the loop, but at least it will reduce the overall effort involved quite a bit. That's the broader idea. So the main challenge in terms of building such a database is curating a training set to start with. I mean, there's no, so when I say training set, we want articles labeled as privacy incidents, as non-incidents. We want to start from, it's not like we can't do it completely unsupervised. So the first challenge is how do we curate such a set. And then we want to engineer features in the data set. When we're talking about just textual data, and engineering features is always a challenging thing when it comes to textual data. And finally, the evaluation is also because it's a problem that is not being addressed before, or it's specific problems where there aren't existing solutions already. How do we define some baselines to say that actually what we're doing is better than what baselines do? So the three main challenges. So in order to curate a training set, we used three sources. So we started with the articles that are already in the database because they were already evaluated by multiple experts to see whether they should go into the database or not. And then we, like using the New York Times News API, we collected about, I believe, 500 or so articles which were tagged with privacy. The New York Times articles are tagged with certain keywords, but not everything tagged with privacy is necessarily a privacy incident. And then we also randomly selected articles from both New York Times and Guardian, which were, the idea is that the random articles mostly they were negative sets, so they were not privacy incidents. And on these, a subset of these articles, like we have about half of them, we had two coders go through each of them and decide whether it is a privacy incident or not. And we had substantially high agreement between the two coders. So that's why we decided for the remaining half of the articles, one coder would tag them as a privacy incident or not. So we ended up having a positive set which had 543 news articles, the privacy incidents, and a negative set having 781 articles which are non-privacy incidents. So In terms of the text processing or the classification pipeline that we built, everything here is mostly, so we have used things which are available, and we have put them together. There's no new algorithm as such, but the pipeline is what is novel. So again, when it comes to, so we have news articles, the text is what we have. So we identify, we do the standard text pre-processing, you split sentences, then you lematize, you can do parts of speech tagging and ignore non-content words, remove stop words. The standard text pre-processing steps, nothing special here. And then once we have the tokens, so we could use, again we can use unigrams and bigrams, and that's what we're using whenever I say or in here, actually we try with both options when it comes to experimentation, because sometimes one may work better than the other. Similarly, so once we have, so the tokens on each unigram or bigram, that's a feature in the data set. And the feature value we're using the TF IDF scores. The TF is the time frequency and IDF is the inverse document frequency. I'll tell a bit about that. Essentially, you're taking a text document and representing it in the vector space, because all the algorithms that we're going to apply, they work in vector space. That's the basic idea. And like I said, so that's like I said, we use a bag of word representation where every token is a feature, and term frequency is how. So if a term occurs in a document, then the term frequency is non-zero. So we use logarithm scaling because it's the Zipf's law. I mean, if a word occurs multiple times, it's not necessary that its importance in the document is linearly related to that. And similarly, IDF is if in the entire data set, if the word occurs in fewer documents, then the inverse document frequency is higher. And the broader intuition is that when you take the product of TF and IDF, you have both the notion of originality and how useful the word is. So, but I think the challenge is, like I said, we end up having too many features. If you just take, if you only take, there are like close to 60K words in the document. Even after pre-processing, we end up having 34K. If you use bigrams, then we have like about 500K features. That's like too big. And the problem is, I think we were listening to the talk earlier. I mean, one obvious problem is computational efficiency. Too many features is too difficult to compute. But when you have fewer sample but features of this high dimension, then it's prone for overfitting. That's, I think, a bigger problem. So we have to reduce the feature space somehow. So what we do is we use mutual information as a measure of determining how important a feature is for this particular problem. So I mean, although the formula may look a bit intriguing, there's not much going on there. I mean, if you just look at the top term, the probability of ET and ET, so the term being in a particular class. If the term is independent of the class, and then that probability can be the product of the two, then it becomes, the logarithm becomes log 1, 0. So essentially, if a term is independent of the class, then the mutual information is very low. It is dependent on the class. If a term occurs only in one class, then the mutual information is very high. So, and these are based on, in our data set, these are some of the top features which are ordered by mutual information. And when you look at it, actually it does make sense. And I think there were also, I think we were surprised when we saw the print April, that's a bigram there. And then we noticed that several articles in our data set were about the Apple incident. And there was a clause in most of these articles at the end saying actually you can find a print of this in the April issue of whatever. So that's how that term ended up. And we removed some of them when we found them. But I think this we found that since we didn't have a separate temporal feature, this can also serve as like a useful thing. So that's what we had. So, and then when it comes to classification, again, we're just using things out of the box. We compare naive Bayes, SVM, and random forest with the different combinations of feature sets that we have. To evaluate how well these things are working, we use the standard classification metrics, precision, recall, and F-measure, and then we do it on tenfold cross validation. Like I said, our challenge is actually how do we say, how do we compare what we're getting, so what are the baselines, right? So one obvious thing to do would be, and I think it works fairly well if you don't have anything. So just see whether the article has the word privacy or not. Maybe that in itself is a good indication of whether the article is about privacy incident or not. So to start with, we thought that that's a good baseline to compare how we are doing. But we can even take that further. Don't just restrict to the word privacy and add more and more words that are likely to infer whether something is a privacy incident or not. So just look at the entire set of positive articles and take the top K keywords and just use those keywords to determine whether something is a privacy incident or not. So we can also do it more sort of a domain independent way, not data set specific way. We can use other taxonomies, like Solo has a taxonomy for privacy. So we can take the categories and subcategories, the names themselves as the keywords, and see if we have a set of keywords based on Solo and use these keywords as indicators of whether something is a privacy incident or not. How well does it work? So when it comes to results, first actually we see the mutual information based feature selection that we're doing. I mean, does it help some way? The x-axis is the 2 to the power scale, where we are experimenting with multiple features. We note that after some time both precision and recall decrease if we add more and more features, which is good in the sense we don't really need those features. Wherever we see precision and recall peak, it's about 8,000 features. Although potentially they can be, like I said, close to 500k features, we can just take 8,000 features, and that works better than using all of the features. So that's the threshold that we're going to use for the rest of the results. Then again, we compared with various combinations of unigrams, bigrams, and TF or TF IDF and scores. We found that just using both unigrams and bigrams, just the TF score works pretty well with a mean F measure of about 93%. So this is just different combinations. Like how do we compare with the baselines? In general, the SVM based TF IDF things work pretty well. For the privacy class, the precision was like as high as 96%, and the recall was about 90%. So with the keywords, we noticed that with the privacy keyword itself, we can do as well as like an F measure is like 81%, but it's still pretty good. But compared to that, we're doing at least like 10% better. So when we add more and more keywords, we see that the recall would increase. That's obvious because the more and more things come into picture. At the same time, precision reduces quite a bit. So that means the keyword-based ones are not necessarily effective, even if you add more and more useful keywords. So that's the overall result. Broadly, some of the directions that we're thinking in terms of doing more analysis. So the one challenge now is, we have a data set, and our thing works pretty well. So developing better and better algorithms is challenging because once you already have 93-94%, it's difficult to improve that just based on technological improvement. So one thing might be we need probably more and more gray kind of articles, the articles that are difficult to classify. So that's why we need a better training set to see if we can develop better algorithms. And also, so far we've only done one type of classification. We can do more finer kinds of categories, not just privacy versus non-privacy. We can try to do privacy versus security, for example, or within privacy, different types of categories. And also more analysis like recognize the entities in the incident and so on. Yeah, so next steps, like I said, I think one main thing is we want collaborators both to contribute things to the database and also use it to do more interesting kinds of analysis. And that's it. Thank you.
Question.
Hi, thank you for your presentation. You might have considered this already, but there's a very rich database for cybercrime at CERT. Have you considered that database?
Cybercrime, I'm not familiar with that database.
They've been collected for more than 10 years, and I think if you had a chance to look at that, that would really augment your data sources. But I also think you'll be able to see a flux in the terminology changing as you suggested.
Right.
So privacy is the hot word now, but before it was breach, before it was
Right.
other things. And so that's just a suggestion that I have. Is, there's a very nice mirroring field between the Cybercrime Center with their large database that they've been checking for a long time.
Yeah, that's useful. Thanks.
I'll comment about that. Dr. Staden, who is the Activist Project, she definitely is aware of that. And what she's trying to do is make a privacy version of that.
Yes, I think it would be
They don't want inside, right?
And I think I take your point in the sense that instead of just looking through news articles, if we can take all articles in the cybercrime database and try to do whatever analysis or whatever classification we are trying to do with that, we may have like that's exactly what I was talking about. There may be more gray articles there. Yeah.
One more question. I was just interested looking at the results.
Yeah.
You showed that the SVM performed better.
Yeah.
My understanding is that the SVM can be sometimes harder to interpret depending on your data. So how did you account for that? Because you did mention how did they perform, but I was more interested in how did you interpret the results.
So among the three classifiers that we compared, it's obvious that naive-Bayes may not work well because we have so many features and we just treat them as independent of each other.
I understand you have a larger data set, so naive-Bayes wouldn't, I think.
So we have a larger feature space, but we have only like 1,100 samples.
And
So we
naive-Bayes
do have.
wouldn't perform good in that, yeah.
So I wouldn't think it would do well because I think there are so many features and treating them as independent of each other doesn't necessarily work well. And SVM is known to work well when in like specifically cases like this where you have a large feature space compared to the number of samples that you have.
Yes, I got that part, but how did you interpret that on your results? Like, what was the interpretation?
So
I'm just asking because I'm trying to figure it out. I know with SVM, it's usually the challenge is how you interpret. That's the challenge. I know it performs better as an algorithm.
So interpret meaning interpret why it is perform better?
Yes.
I think that's, yeah, I don't have an easy answer for that.
Okay,
But
we
most
can
of-
talk about it offline.
Yeah.
Okay, great. Thank you very much.